So in today's video, we'll be looking at converting stoichiometric tables for batch reactors. So now with the conversion, when we say conversion, let's say we have a reaction A plus B going into C plus D. Now when we're talking about the conversion, you want to look at the amount of the reactant that has been able to be converted into product. Right? So in a case where you have two reactants, you can find a conversion for both reactants and then use it as the conversion for the actual reaction taking place. So what we have to do is that we have to find for the limiting reactant and then we find a conversion based on that limiting reactant. Because when you have any reaction, right? So let's say 20 moles of A present, 30 moles of B initially present, and then we are reacting them. Their coefficients or their stoichiometric coefficients are 1, 1 for each. When you are reacting them, definitely A is going to be used up first in the reaction because it has the least amount of moles present. So when A gets used up, so now you are left with only B in the reactor, right? And now B will be in excess of 10 moles. Now with B alone can't form C plus D. So now the reaction comes to an end or the reaction stops. So when you want to find a conversion, you're going to find a conversion based on the reactant A. So with the conversion, you are trying to see that we want to find the amount of A that has been converted into product or the amount of A that even took part in the reaction. Because when you have any reactant, not 100% of the reactants is going to take part in the reaction, right? So let's say we have 100 moles of A present. So we are assuming A is our limiting reactant, and then we are assuming that 80% of A was converted or reacted to form the product. That means our conversion is our 80% here. So it means that 80% of the 100 moles of A was converted into product and we are left with 80 moles. So this tells us that 80 moles of A reacted out of the 100 moles. And what to be the moles unreacted? The moles unreacted will be 100 minus 80 and that will be 20 moles. So it means that for the product side, we'll be having part of the reactant present, right? A, but then A has 20 moles here. And that is why for every product, you have to purify it or you have to separate it because some of the reactant might be in the product. That's in a case where the conversion is not 100%. So how can you deduce the conversion? The conversion for A, we are representing that with X is equal to the initial moles of A present. I'm using moles because we are dealing with batch reactors. So the initial moles of A present, which in this case is 100, right? Minus the amount of or the moles of A that did not react or the moles of A that was found in the product. So minus Na. So in this case minus 20 divided by the initial moles present, which is 100 in this case. And this becomes the conversion of A. So in this case we get 80 over 100 and that is 80%. That was actually the conversion we assumed. Now, in the case where B is our limiting reactant, then I'm going to say NB naught, which is initial moles of B present, minus moles of B all over moles of B naught. And this becomes our conversion for B. Right? Yes, so that's actually what we are calling as conversion and then our limiting reactant. Now, how do we determine whether this particular reactant is the limiting reactant or this is in excess? So we come again when you have A plus B going into product, right now you're not interested in the product, and then initially you have 20 moles, you have 30 moles. Determining which reactant is the limiting reactant or the excess is not always dependent on the initial moles present, right? For this particular reaction, it will be dependent on the moles present, and then we are going to look at that shortly. So determine the limiting reactant. The easiest way to go about that is that you have to know the initial moles of the reactant present. So in this case, you know the initial moles of E and E naught, initial moles of B and B naught. What you have to do is that you just have to divide that by their stoichiometric coefficient. So in this case, A is 1 and B is 1. So just 1, 1. And then we are left with our NE naught and then our B and B naught. Right? The moment we divide by our stoichiometric coefficient, the one with the least becomes our limiting reactant. So when you divide by 1, we still get 20 because 20 over 1 is still 20. And then when you divide the 30 by 1, you are still going to get 20 and then 30. So now our final answer is what we are going to use to determine this is our limiting or reactant. So then A becomes our limiting. And that is why for this, A was our limiting reactant. In the case where we have A plus 2B going into C plus D, and then we have 20 moles of A present, 30 moles of B present. To find the limiting reactant, so 20 over 1, comparing that to 30 over 2, we get 20 and we get 15. So that means our B is our limiting reactant. So it means that when you have this reaction and you have 20 moles of A present and 30 moles of B present, B is going to be used up first. You can even do that using the mole ratio, or you can just you can just look at the reaction and then determine it. But then to be very, very sure of your answer, just divide through by their stoichiometric coefficient and then you will come to a good conclusion. So with this, when you want to use your eyes to just check through the reaction, you can see that A plus 2B, right? And then you realize that for every 1 mole of A, we need 2 moles of B to react before the reaction occurs. So anytime the B is not actually in a very large amount as compared to A, then B will always be the limiting reactant, right? Because you are seeing that you have A and then you have B. But for every 1 A, you need 2 B to react. So if you are putting 1 mole of A, you need 2 moles of B. When you are using 10 moles of A, you need 20 moles of B. You realize that if 30 moles of A was present, right, and then 20 moles of A was present, to find the moles of A to react completely with the moles of to find the moles of B to react completely with the moles of A here, when you are using 20 moles, you need 40 moles of B. But then your B is not even 40 moles, so it's 30 moles, right? That's to tell you that your B will rather be the limiting reactant. Or you can just divide through by their stoichiometric coefficients and then you can use that. That one always works too. Now, so we go to our stoichiometric table. But before that, what's the design equation for batch reactors? We know that for batch reactors, from our previous video, we are very much interested in the time, right? So we had the design equation to be T equals integral NA naught negative NA naught to NA from the NA over minus RAV. And instead, this minus here simply indicates that it's the rate according to the reactant, where A is our reactant. Now we want to write the design equation in terms of conversion. So Na here is the moles of A, right? And when you compare that to this, realize that our Na here is actually our moles of A that did not react. So to find our moles of A that did not react, so from this, conversion is equal to Na naught minus Na all over Na naught. So we can just make Na the subject here and see that our Na here would be, so Na naught Xa is equal to Na naught minus Na. So we can make this the subject. So Na is equal to Na naught minus Na naught Xa, right? So this is the amount or the moles of A that did not react, and that will be equal to the initial moles of A present minus the amount of or the moles of A that was converted, and the moles of A that was converted. So this is moles unreacted is equal to initial minus moles converted, and the moles converted will be the initial times the conversion, right? And this is the conversion. So we realize that our Na is equal to Na naught minus Na naught Xe. we can factorize Ne naught out, and then we'll be left with Ne naught 1 minus Xe. And then having this, we can actually find, this is the Ne, right? We can just find the Ne against the Xe. So we want to differentiate this reaction with respect to Xe, right? So when I'm differentiating, let me just split this part, or let's say from this, you can differentiate that, or even from this, if your differentiation actually works. So with this is a constant and it's multiplying, so that remains, and then we'll multiply that with, we differentiate what's in the bracket, right? So we are differentiating with respect to Xe. When I differentiate this with respect to Xe, I get -1, right? So I get the Na over the Xe is actually equal to negative Na naught. And then I can put this here. When I put this here, I get the Na is equal to negative Na naught dXA. And then I can put that here and say that my batch reactor time is equal to negative. Now, because the N here has now been shifted into dXA, we can put Na naught here and Na here. However, to change the limits, we know that at Na naught, which is initial moles of A present, our conversion will be 0, right? Because if there is no conversion, that's when you actually get the actual moles of A initially present. And then at Na, our conversion is at a certain conversion, Xa, right? So from Xa naught, right, or because the conversion is 0, so from 0 to Xa, and then we'll put our DNA there. So our DNA is now this. So negative Na naught dXA all over negative RAV. Now this becomes our design equation when we have our conversion. So our negative here will give us positive, right? And because our Na naught here is a constant, because the initial moles doesn't change, and that's why it's not even affected by the D, because D here is a differential, which is a small change in something. But then our Na naught here will always be a constant. When you have a reaction, then you are seeing that you are feeding in 20 moles of A. So it's always 20 moles of A. The initial moles wouldn't change. But then the one coming out will rather change based on the conversion. So you can bring our Na naught out here. And then because this is negative, they give us positive. So Na naught integral from 0 to Xa dXA over RAV. So we are left with this. T is equal to Na naught integral from 0 to Xa dXA over RAV. So now this becomes our design equation. We can use this or the previous one, which is T is equal to minus Na naught to Na dNA over negative RAV. So you can either use this or this to find the batch time. Sometimes the question can be the form that you have to find the time necessary to achieve a certain conversion. And to do that, you are going to use this equation because this has conversion in it, right? And sometimes you might be asked to find the moles you made after a certain time in the batch reactor, and then you can use this. However, you can still use this, but then after this you have to solve further before you can get what you want. But then when you use the specific equation, you just get your answer straight away. We'll be 7 more questions on that. So we are done with the conversion. Now let's come to the stoichiometric table. So stoichiometric table for batch reactor. we are still looking at batch reactors. Now, so when you have any reaction A plus B going into C plus D, and each has a specific coefficient, so C, D. So first of all, what you have to do is that you have to find your limiting reactant. And then, so we are assuming that our limiting reactant is A. Now, once you get a limiting reactant, then we then have to express all the other reactants in the product in terms of the limiting reactant. Right? So we just have to divide through by A, by A, by A, and by A here. So now we are left with A plus B over AB going into C over AC plus D over AD. Right? So this now what you'll be actually working with. And we write down our species, right? So our species here we have A, B, C, and then D. Right? And then our next one is our initial present. So for A, our initial moles present is Na naught. For B, that will be Nb naught. But then because we are writing it in terms of the E, which is the limiting, we can say our Nb naught will be the same as Na naught times, so our Nb naught will actually be the same as Na naught times Nb naught over Na naught. Right, so this cancels this and we are left with this, which is our Nb naught. That's what we are actually doing here. And then because we are dividing through by E, that's why we want to bring this one inside. So we define another parameter. So let's say phi should be equal to Ni naught over Ne naught, where your Ne naught is your limiting reactant, the initial moles of your limiting reactant. In this case, you are using A. Your Ni naught refers to the initial moles of all the other species present. So if I want phi of B will just be Nb naught over Na naught. If I want phi of A itself, I'm going to get Ne naught over Na naught, and that will give me 1. Right? So realize that with our Nb naught that we have here, saying that it is Na naught times Nb naught over Na naught, this portion can be written as phi b, and we see that our Nb naught is equal to Na naught phi b. Right? So we can just put Na naught phi b here. So with our C2, if there is initial moles of C, so sometimes you can have a reaction that we have a trace of the product already in the reactor, right? So our initial moles of C present will just be, which is our NC naught, will just be Na naught phi C, right? So just like we saying Na naught times NC naught over Na naught, and this cancels this and I left it to this. We are then representing this with our phi C. This one too, we can just have phi A, but I don't want to be the essence because phi A is just 1. So this one, so we are going to get initial moles of D present to just be Na naught phi D, right? And this is what we have here. Now, anytime there is an inert species, so we'll consider the inert species later on. You know that the inert species doesn't actually take part in the reaction, right? So now to consider the inert species, you can see that if you are using I to represent our inert species, the initial moles of the inert species will still be Na naught phi I, right? So where phi I is equal to initial moles of our inert species all over moles of A. So this multiplies this, and then you are getting this back. So let's put our inert species here. Na naught phi I. And then we can consider our change. So our change here, we are referring to what are changing our initial moles now. So all the reactants, there will be a negative change. because when you have 80 moles of A present, and then now we are getting 20 moles at the end of the reaction. So the change is what? Negative 60, right? Because change is always final minus initial, and then your final minus initial will give you negative. So the change for all the reactants will always be negative, and that of the product will always be a positive change. Yes, that's one thing you have to take note. So now with the change for the reactants, it's just going to be our initial moles times our conversion. Because now we said our conversion is based on our limiting reactant. So all the conversion we'll be using here will be based on the limiting reactant. So our conversion will be based on the limiting reactant. So now for A, the change in A will just be negative NA naught times XA, where our X is the conversion of A. Because our A is our limiting reactant, so all the conversion will be based on A, right? And then for B, so the change in B, we can't use the initial moles of B present. Why? Because when you have a reaction, right, and you are saying that A is our limiting reactant, so the conversion is based on A, right? So you are trying to say that for the whole reaction, the conversion is, let's say, 80%. So it means that if you have 20 moles of A present, your conversion for A will be just 0.8, which is the 80%, times your 20, and that will be 60 moles of A was converted. Now for B, if your B is in excess, so let's say you have 30 moles of B, you can say that B conversion for B is 80% that of the 30, because the conversion is actually based on your A, not on your B, right? Because your B is in excess. Now to find the conversion for B, that's why initially we try to find the moles of B all based on the limiting reactant by dividing through by the coefficient of A. Right? So in that case, we are going to get something like negative B over A, right? Which is this times initial moles of A, right? And times our conversion. Because our conversion will always be is based on the limiting reactant, we can't use times XB here, right? Initially, I told you guys that for a reaction that involves two or more reactants, you can't have conversion for both A and B. It doesn't work that way. So you have to find a conversion for the limiting reactant. You're going to find a conversion for the limiting reactant. That's what you're going to use throughout your reaction. So even for B, we have to express the moles of B in terms of the limiting reactant, and that is B over A times the initial moles of B. So what you've done here is that you are trying to convert the moles of B into the moles of A present, and then we can use the conversion of A here. So for the product too, we are going to do the same thing. So just C over A, and because they are product, the change will be positive because the output will be higher than the input. Right? So that will be a positive C over A, then N A naught X. For the D also, just D over A, N A naught X. So conversion of A, conversion of A. And then for the inert species, now because the inert species, it doesn't form part of the, it doesn't take part in the reaction. So the amount of the inert that is entering will be the same amount of the inert that is coming out, right? So there is no change. So we just put 0 here, there is no change, right? Because the output and the input will always be the same. So you can put 0 here. And then let's find the remaining. So the remaining is the output minus the input. What we are left with is your remaining, right? So when I have 100 moles of A entering and then 20 moles coming out, the remaining will be 20 moles which is coming out. And then if you are saying that the change, so the change will be output 20 minus 100, which is negative 80. If the change is negative 80, to find the remaining, I'm just going to add the change plus my initial moles present, and that will give me the 20, which is the remaining. Right? We are going to do the same thing here. I'm just going to add a change to the initial. So with the remaining is going to be will just be n, sorry, for a, n a naught minus n a naught x a, right? And I can factorize n a naught out, and I'll get n a naught 1 minus x a. And this is the remaining. And realize that initially we solved for NA, and then we had NA being equal to NA naught 1 minus XA. And this actually from this. So this becomes the remaining. And then for your B, the remaining of B will just be, your B is now NA naught theta B, the initial, right? So NA naught theta B minus B over A NA naught XA. So we have this. And then we can factorize NA naught out. When you factorize NA naught out, I'm going to get NA naught out theta B minus B over A XA. Right? So our moles of B remaining will be NA naught out theta B minus B over A XA. So we have this. So for our NC, it's going to be NA naught theta C plus C over A NA naught XA. So then we are going to get NC, the moles of C remaining. So the moles of C remaining will just be the moles of C in the product side, right? So that would be, we can factorize NA naught out, and we are left with theta C plus C over A XA. So this is also the moles of C remaining. Now for the D, so moles of D remaining will also be NA naught theta D plus D over A NA naught XA. So we can factorize NA naught out, and we are left with theta D plus D over A NA naught XA. And for the inert, remaining will still be the same as the initially present. So just NA naught theta I. So Ni is equal to NA naught theta I. So with the initial moles, you can find the total initial moles present. And with the total initial moles, you can actually use this. Initially, we had Na not present. And for the NB, not present, we were able to convert it into Na not, and we had Na not 5B. For the C, it was NC not 5C. For the D, ND not 5D. And then for the inert, all were in Na not. So Na not 5I. So they all have Na not present. So you can actually factorize Na not out. And then you are going to get 1 plus theta B plus theta C plus theta D plus theta I. And that will be, when you sum them all, you are going to get NT naught, which is the total moles present. Right? So the whole of this is giving us our NT naught. When it comes to the remaining is also simple. You are finding the remaining of A, B, C, D, and the inert. So that was also going to be Na naught 1 minus X, which is XA, right? Plus Na naught theta B minus B over AX plus Na naught. So this is for B, this is for A. You are doing C, theta C minus c over ax. I'm using x, not xa, because I've already said this, that anytime you have a reaction, the conversion is actually based on the limiting reactants conversion. So whether xa or x is still the same. So this is for c. And then for d, you're going to get na naught theta d minus d over ax. And then for the units, it will still be the same, na naught theta I. Right. So you realize that writing them is very easy. You don't have to drive in all the table all the time. So anything you want, you can just write it straight away. You just have to understand what you are doing. So with this, you can factorize na naught out. So when you factorize na naught out, we get 1 minus x plus theta b minus b over ax plus theta c minus c over ax plus theta d minus d over ax. We just factorizing na naught out plus theta I. So let's group like terms for na naught. We can have, let's put in the theta parts. So we have 1 plus, we skip 2 theta b plus, we skip 2 theta c plus, we skip 2 theta d plus, we skip 2 theta I plus, and then we come back to our x's. So negative x, negative b over ax, negative c over ax, negative d over ax. Yes, and that's all. Right. So we can see that we have 1 plus theta b plus theta c plus theta d plus theta I here. And then here nt naught is na naught multiplying 1 plus theta b plus theta c plus theta d plus theta I. We can actually fit nt naught into this. But to make it very easy and then clear enough, this is what I'm going to do. We know that you can, the na naught here multiplies everything in the bracket, right? So we can have na naught here, it will multiply 1, we get na naught. To multiply this, we get na naught theta b, blah blah blah. So we can just put in na naught here, multiplying 1 plus theta b plus theta c plus theta d plus theta I. And then we put our bracket close here, plus, and then na naught is still going to multiply the whole of this. So negative x minus b over ax minus c over ax minus d over ax. So the whole of this is what is our nt naught. Right. This here, we are finding the total moles remaining, right, which is our nt. Just like when we want to find total moles of A present, we just write Ne. So this is our nt. Our nt naught here is total moles initially present, which is for this portion, plus. So now let's come to this part. We have Na naught multiplying the whole of this. We can still factorize x out from this. And when we are factorizing x out, we are going to get, yes, so when we are factorizing x out, we are going to get negative 1, right? So negative 1 minus, sorry, this were plus, right? For the product, they were plus. I missed something. So plus, right? So I said this, that the products are plus, the chains they are positive, but then the reactants are negative. So C plus C, right? So we have plus here, plus here. So we can factorize x out here, and we are going to get x into bracket negative 1 negative b over a plus c over a plus d over a. And then we can have our na to be nt naught plus. So now we have our x also factorized out. So na naught x multiplying what we have here So what you have here, you just put, you you are writing them all to bring the product first because they are positives. So C over A plus D over A minus B over A minus 1. Right. So we have this term. Now this term, we can replace this term with lambda and see that lambda is equal to C over A plus D over A minus B over A minus 1. And then we have our NA is equal to NT naught plus NA naught x lambda. So the whole of the stoichiometric table was actually to establish the fact that NA, sorry, did I say NA? NT, NT is equal to NT naught plus NA naught x phi. So this is what we wanted to establish. Anytime you are given a question, you don't have to go through all the steps to derive the answer. You just have to keep the formulas in your head. So you should know this, very, very important. And then you should know that your NA is equal to NA naught 1 minus XA. Like these basic things. You don't have to derive all the stoichiometric tables. So, but then if you know how to derive them, it becomes on your fingertips and then it's easy to recall them. So this is what we want to establish. So our theta here, so our lambda here, when you have any reaction, so anytime they give you a reaction, let's say A plus B plus C going into D plus E. So this A, B, C, D, E. When A is your limiting reactant, you just divide through by A, A, and A, right? Your lambda then becomes D over A plus E over A minus then the reactant. So 1 minus B over A minus C over A. So this becomes your lambda. And then just have to put in E. So this is what we have. Now for batch systems, you are looking at batch systems. Concentration is actually equal to moles over volume, right? So if I want the concentration of A, it's going to be moles of A over the volume. If I want initial concentration of A, now we understand what Ca means and what Na means. So Ca here represents moles of concentration of A remaining. This is moles of A remaining. If I want initial concentration, it's going to be Na naught over V, right? Yes. So we should also keep this in mind. And next video will be solving more questions on the batch reactor before we even proceed to our continuous flow reactors. So we can go ahead and derive certain things here. So we have liquid phase reactions. And then we have gas phase reaction. So with the liquid phase reaction, if the reaction is actually occurring in a rigid steel tank or in a rigid reactor, so in a rigid reactor, it means that our volume is constant and doesn't change. So our V will always be equal to our initial volume. This is our volume of the reactor, wouldn't change. So when I want to find the concentration of A, which is, I'm using A as any species, right? The concentration of A remaining will always be the moles of A remaining all over the V. And this is equal to, we know what Na means. So Na is equal to, in terms of the initial moles present, Na naught 1 minus X. I'm using X because now we have a fixed conversion, and that conversion is the conversion of the limiting reactant, and that's what we use throughout all over. My V here can still be V naught, right? Because we are seeing that the volume is constant in a rigid tank. So V is equal to V naught. And mostly for liquid phase reaction, the volume doesn't change, right? So we can just put in our V naught. And then Ca naught over V naught here gives us Ca naught initially present. So multiplying 1 minus x. So we realize that for even concentrations, concentration of A remaining will also be equal to concentration of A present, initially present, Ca naught 1 minus x. And that is equal to Na is equal to Na naught 1 minus x. Realize that the equations are the same. Now let's come to B, where B is not the limiting reactant. So to find the concentration of B remaining, it's just going to be NB over the V. So this is where the stoichiometric tables application comes in. What is our NB? You know that our NB is the remaining, and then from our stoichiometric table, NB is equal to Na naught multiplying theta B minus B over Ax. Right? So this NB. So that's where you should apply the stoichiometric table. Right? So our Cp now becomes Na naught multiplying theta B minus B over Ax. This for the NB portion. All over our V. So our V here you can write as V naught because we said V is equal to V naught for liquid phase reactions. Or if it's not a liquid phase reaction, but it's a gas phase reaction, and then it's a rigid reactor, then this still holds. But then if the question doesn't say that it's a rigid, but then we are dealing with liquid, then V equals V naught still holds. But if the question does not mention that it's a rigid tank, and then we are dealing with a gas phase, you can't assume this. There's also a way to go about it, and then we'll look at that one too. So our Na naught over V naught is Ca naught, right? Multiplying theta B minus B over Ax. Now we have this. So now for Cb, Cb is equal to Ca naught multiplying theta B minus B over Ax. Now this is when our x is the conversion of A, not B, right? So someone might ask that, so why is it not Cb is equal to Cb naught 1 minus x? This is actually wrong. This actually holds when your x here is the conversion of B. But then if B is not your limiting reactant, that means the conversion here is not for B, it's for A. That's why initially I was writing A to show that this is actually for A. But now that we've understood that the conversion here we are using here is the conversion for A. Anytime we want to find Cb, this works. This actually works. Cb is equal to Cb naught 1 minus xb. When you write this, it is correct. But because you can't write a conversion for each of the reactants, we have a standard conversion we are using. And that conversion is the conversion of the limiting reactant. So to do that, and because B is not your limiting reactant, you can't use XB. Right? So you just have to convert it into Ca naught. And that is why, and that is when your stoichiometric tables application comes in. So theta B minus B over Ax, where your x here is actually Xa, conversion of A. So this. The same thing applies. You can derive further for the product too. So if I want to find C of D, which is my product, it's going to be ND over V. I know what ND is. So ND is Na naught multiplying theta D plus D over Ax all over. So my V can be my V naught. And then this portion give me Ca naught multiplying theta D plus D over Ax, where this x here is for Xp, the limiting reactor. So that's the application of the stoichiometric tables. And next we will be solving more questions on stoichiometric tables. And now let's go to our gas phase reaction. We looked at liquid phase reaction. Right? Now what if you have gas phase reactions? Now with a gas phase reaction, we are trying to see that our V is not equal to V naught. So our volume is not equal to our initial volume, right? But for the liquid phase, the volume is always constant throughout. But for gas phase reactions, we can't say same for that. Right? So now how do we do that? you have to. So now when V is not equal to V naught, then what is V actually equal to? You have to do some derivations here. And because we are dealing with gases, we can always turn back to our ideal gas equation, which is PV is equal to ZnRT, right? So we can have this. So this always works. And then we will say that for ideal gases, so PV is equal to, we can put nRT here is equal to Z. So our Z doesn't change, right? And we can just put initial. So if this is a constant, it doesn't change. So initial Na not initial T initial. Our ideal gas, this is a constant, and this should be equal to Pa at a certain point. Well, let me just write PV over, just like me writing V and then V naught, over Na. So I think I should put in just Na and then R and then the T. So I'll just put T instead of putting T. Because if I put T, it becomes like temperature of the A, But you're looking at initial and then temperature at a certain time. Yes, so we can have this. And then because Z is constant, initial conditions and final condition will always be the same. So P naught V naught is equal to N naught R T naught, and this is equal to P V N A R T. And then we want to find the relation between V naught and then V, or V and then V naught. And that's what we want to do here. So we can just make V the subject or V naught the subject, or any of them should work. Right? So we put in V is equal to, and then we can have NART P naught V naught all over N naught RT naught, and then we can R and R will cancel out. So we can have V is equal to NA over N naught. So we have this N naught, NA over N naught multiplying, and then we can have T over T naught, and then we can have P. So I did P camp, so all over P. So P naught over P. So this are NA, this our T, this are P naught. So times V naught. So we get V is equal to NA over N naught, right? Multiplying T over T naught, multiplying P naught over P. Sorry. So this is P naught over P here. So P naught over P here. Why did I put P naught? So P, so from here. No, we are making V the subject. So it's supposed to be NAR P naught over P. Yeah, so P naught over P. So there is no P here. So P naught over P multiplying V. Now this is actually the relation between them. Now how do you find the ratio between NA over NA over NE naught? So this is supposed to be NE naught, right? Yes, this is constant. So anytime you are dealing with isothermal, so isothermal reaction where the temperature is constant, so your T is equal to your T naught. Then we are going to get V is equal to NA over NA naught. Your T and T will cancel out, so P naught over P times V. Anytime you're also dealing with um adiabatic, or let's say isobaric processes too. So for isobaric processes, P naught is equal to P, and then that part also cancels out. So you are left with V is equal to NA over N naught. NA over N naught multiplying. Did I use? So let's see, let me finish this and then correct that. Multiplying T over T naught, right, times V. Anytime you're also dealing with um both isothermal and then isobaric. So where P naught is equal to P, T is equal to T naught, then I'm going to get V is equal to just Na over Na naught times V. So this is what I want to correct. Now, for the gas phase reaction, with the PV is equal to nRT, let's look at the moles. Let's look at the total moles, because the pressure and the temperature here is not like you are finding the pressure of just pressure of A, but you are looking at the pressure of the whole reaction. So our Na naught here is supposed to be our Nt naught, right? The total initial moles. Our N here is supposed to be our total moles remaining. So this is what I want to correct. So T naught and then T naught and then T. Right. So T naught. So this is what I want to do. T and then T naught. Let's look at the total moles, not moles of A alone. T over T naught. T over T naught. So this is T over T naught. Right. So we need the total moles of what's actually occurring in the reactor, and then the total moles remaining, and then the total initial moles also. Now we can make some derivations here. From the stoichiometric tables, we derive that. Now we said V is equal to Nt over Nt naught multiplying V. And we said that this is when we are looking at isobaric and isothermal both occurring. From our stoichiometric tables, we derive that Nt is equal to, which is the total moles, the total moles remaining. We derive that Nt is equal to actually Nt naught plus Na naught x. Is this sigma? Yes, sigma. And then with our Nt naught, we had it to be just Na naught multiplying 1 plus, I think we derive something like 1 plus theta A plus theta B plus theta C plus theta D. I think we had something like this. Yes. So this becomes our Nt naught was this. Na naught multiplying 1 plus theta A, theta B, theta C, theta D. So when you want to find the ratio between them, you can just put in V is equal to, our Nt is Nt naught plus Na naught x times V all over. And then our Nt naught is Na naught, or you can just put in Nt naught here. So let me just put in this sigma. So Nt naught, and then we are going to get V is equal to Nt naught over Nt naught plus Na naught over Nt naught. You see now we've gotten Na naught here, multiplying the conversion times sigma, everything multiplying V, right? And then you can go ahead and see that Nt naught over Nt naught give us 1. So 1 plus Na naught over Nt naught multiplying x sigma times V. So our V is equal to, now before that, let's pay attention to this term. We have this term here, Na naught over Nt naught. So anytime you have the initial moles of a certain species all over the total moles present, what comes into your head? So we get mole fraction of A naught. So the initial mole fraction of A present. You can just put that there. So V is equal to 1 plus. So this Ya naught is this portion alone, multiplying x sigma, everything times v, right? Now, y a naught times the conversion is equal to epsilon to a certain time. So this is what I actually want to establish. So it's equal to epsilon. You can, however, put this there, or you can leave it as this. However, you should know what you are trying to say, that your initial mole fraction of A, which is your limiting reactant, times X should give you this portion, should give you this, which is epsilon. So we get V is equal to 1 plus. So this is representing this portion. Times this portion, your sigma, right? So y a naught times your sigma should give you this. So this is representing this portion. So sigma x times v. Now we derive this. Sorry, v naught. So everything is v naught. We derived this based on the assumption that it is isobaric and then isothermal. Now in a situation where it is not isobaric and isothermal too, then the general expression becomes T over T naught. So I just recalling this. T over T naught multiplying P naught over P, multiplying this portion V naught. So if it is isothermal, this part goes and I left it to this. If it is isobaric, this part goes and I left it to this and this. If it is both isobaric and isothermal, this both of these go and I left it. V is equal to 1 plus epsilon x V naught. So this is also what I wanted to establish. This is for gas phase reactions. So for gas phase reaction, you should have this in mind, that your V is not equal to your V naught, but then your V is equal to 1 plus epsilon x, and then epsilon is equal to y naught, y e naught sigma. You can find your y e naught by putting m e naught over the total initial moles present. This sometimes when they tell you that for maybe there is a reaction and then the reaction involves pure A, right? So the feed is a pure A. So the moment you hear that the feed is a pure A, that means your y A naught is equal to 1. Yes. But then if there are inert species present, then you know that inert species is going to take part in the total moles. So then your y A naught wouldn't be 1. Right? But then the moment you hear pure feed of A, that means the total moles initially present is made up of only A, and then the mole fraction of A will be 1. And then we know what the sigma represents. I think we've derived that using the stoichiometric tables. We say that our sigma is equal to the product, right? So let's say D over A plus C over A minus the reactant 1 minus B over A. Yeah, so we derive sigma to be this. Right. So this is what you had sigma to be. So you just find this quickly. You multiply by your mole fraction of A, and that will give you your epsilon here. And that times the conversion of A. So this conversion is actually the conversion of A. When you add it to and multiply by the initial volume, that will give you the V that we want. But for liquid phase reaction, V is equal to V naught. Yeah, so that will be all for now. Our next video will be solving more questions on the batch reactors.